So, earlier we learned about generating functions. So, if you have a sequence, let us say we denote it by an, n greater than or equal to 0, we can capture the information that is there in that particular sequence of real numbers by its generating function, which we denote by Ax. Okay. So, Ax is nothing but the formal power series A0 plus A1x plus A2x square and so on. So, we saw an example where we looked at a sequence coming out of some combinatorial property, computed its generating function and used the generating function to obtain a closed form solution for the nth term of the sequence. So, today we will look at combining generating functions. In particular, we will look at products of generating functions and understand their significance from a combinatorial standpoint. So, let us look at the following sequence. Let us say we look at two sequences, one is an and its generating function, let us say we denote it by Ax, and there is another sequence Bn and its generating function we denote by Bx. Now, if we define a new sequence Cn which is equal to An plus Bn. Okay. So, the nth term of the sequence is An plus Bn and the sequence is denoted as Cn. Okay. So, for this Cn, what will its generating function be? So, will Cx be equal to Ax plus Bx? Well, it will be, because if you look at Ax plus Bx, the nth term the coefficient of the nth term of x raised to n is equal to so an x raised to n and bn x raised to n are both present in Ax plus Bx, and their sum, which is an plus bn, is going to be the coefficient of x raised to n. Okay, so that's so to add two generating functions is simple. So, if you had two sequences, pointwise addition of the sequences will result in a new sequence whose generating function is simply the sum of the generating functions of the previous sequences. Now, if you take the product of generating functions, what happens? So, instead of looking at Ax plus Bx, let us say if we had dx is equal to Ax into Bx. So, this is going to be dx is clearly a generating function of some sequence. So, if we denote dn by the nth term's coefficient, will this be equal to an into bn? Okay, so, this unfortunately is not the case, but whatever is dn, we will understand that in more detail today and see some example of using this understanding to solve some combinatorial problems. So, the math is very simple. We need to determine the nth term of Ax times Bx, or rather the coefficient of x raised to n in Ax times Bx. Okay. So, if we look at So, we need to compute the coefficient of x raised to n in Ax times Bx. Okay. So, if Ax by definition, if it was A0 plus A1x plus A2x square and so on, and Bx is equal to B0 plus B1x plus B2x square and so on, when you take the product Ax times Bx, which is what we call as dx, this is going to be the coefficient of the constant term is just A0 times B0. The coefficient of x raised to 1 can come from A0 B1 plus B0 A1. Both these products are going to result in x, and their sum is going to be the coefficient of x raised to 1. So, I will write this as A0 B1 plus A1 B0 times x, and the next term, the second term or the coefficient of x square will essentially be A0 B2 A1 B1 and A2 B0. Okay, so there is a nice pattern in the sequence. So, the next term will be A0 B2 plus A1 B1 plus A2 B0 the whole times x square, and x cube term would essentially be A0 Bn plus A1 Bn minus 1 up to An B0 multiplied by x raised to n and so on. Okay. So, dx can be written as summation of di x raised to n, where di is equal to summation k going from 0 to I a k b I minus k. Okay. So, and this is, so the sequence obtained in this particular manner is also called as a convolution of A and B. Okay. So, when you multiply the generating functions, the sequence that you will get from the product of the two generating functions will be a sequence which is a convolution of the two underlying sequences. So, now let us see some particular applications of these. We will see combinatorial use. So, let us say for us An will denote the number of ways of forming some particular object, some particular combinatorial object or structure using, let us say, n elements, and the number of ways of forming a certain structure using these n elements. So, these n could be the letters, I mean say 10 letters or n letters of some particular alphabet, and you want to look at words which can be formed without containing let us say a certain pattern. And Bn is also, so this is for the number of ways of forming a different structure, could be even the same structure. So, it is called as another structure. using n elements. Now, let us look at the following problem. We are given elements 1 to n. Okay. We are allowed to form a subset A containing elements 1 to, let us say, I, and B containing elements I plus 1 to n. And on this set A, form a structure of the first kind, or we will call it as type A, and in this you form a structure of the second type. Okay. And how many ways are there of forming this, and what we are interested in is this whole new object, there are how many ways to form these kind of objects, that is what we want to count. And that can be, I mean, if we denote that by, let us say, Cn, okay. So Cn is a number of ways of splitting a set of n elements into two parts, so that the first part is 1 to, let us say, k, this k is your choice, and then the second part is from k plus 1 to n, and you need to form a structure using the first k elements and another structure using the next elements. The total number of doing this is what we denote by Cn, and what we know is the generating function of Cn, which we denote by Cx, is going to be equal to Ax times Bx. Okay. So this is the combinatorial use of whatever we had learnt about generating functions earlier. Okay. So let us see a more concrete application. So let us say that you are studying in a university and there are n working days. And what is required is you have to split the semester into two halves, and in the first half you have one exam, and in the second half you have two exams. Okay. So the semester consists of n days, and out of these n days you have to select 3 days for conducting examinations, and out of these 3 exams, one exam should be in the first half. So there is a designated first half and there is a designated second half. The first half will have precisely one exam and the second half will have precisely 2 exams. You are free, although we call it as half, we can just split it into 2 parts. Okay. So the first we should probably refer to as the first part. The first part will have one exam and the second part will have 2 exams. There are how many ways of designing the semester with these exams? Okay, that is what we need to compute. Let Cn denote the number of ways of organizing the semester in this particular way. Okay. Now, if we denote A1 or AI, so An denotes the number of ways of designing the first part, and Bn denotes the number of ways of designing the second part, and Cn we can simply by looking at the problem say that Cn is going to be, first you have to split the semester into two parts, and for each part you can design the examination days in whatever way you please, and then you will get the total number. So, that is going to be summation over k going from the first part. K is the number of elements or the number of days in the first part. So, k goes from 1 to n minus 2, because if the first part contains n minus 1 days, the second part can contain only 1 day. That is not going to give a meaningful split with 2 days or 2 examination days, and therefore, k goes from 1 to n minus 2, and a k times b n minus k. So, that is going to be summation k is equal to 1 to n minus 2. A k is the number of ways of picking 1 day out of k days. So, that is going to be k times, take this as n minus k, choose 2 is the total number of ways. So, this is what we need to compute, k times n minus k, choose 2. You can expand it out and work out. So, that is going to be summation k equals 1 to n minus 2, k into n minus k into n minus k minus 1 by 2. So, you can expand out the terms, n is fixed. So, you can take n outside. So, there are going to be 6 terms in the expansion. You can expand out the terms and you will have k raised to 1 and k square and k cube appearing. You can sum it up and you will get some closed form solution. In this part, what we will see is how to do the same calculation without using the formulas for summing up polynomials of degree 2 and 3, etc. We will do it with the help of generating function, okay, because the generating functions for an and bn are fairly easy to compute. Okay, so, what we know is the following, and so this is our approach. Compute Ax, compute Bx, these will be easy to compute, we will see, and then Cx, and since Cn is equal to ak times bn minus k, what we know about the product of generating functions, we can say that Cx will be equal to Ax times Bx, okay, and then from Cx obtain Cn, okay. Because Cn is a convolution of An and Bn, we can just compute the generating function of Cn by just taking the product of Ax and Bx, okay. So, let us see what is Ax. Now, An is equal to k, therefore, Ax is equal to k into x raised to, so this is going to be summation k x raised to k, k going from 0 to infinity, or this is going to be equal to 0 term does not contribute, x plus 1 times x plus 2 times x square plus 3 times x cube and so on, okay, and Bn is equal to n choose 2, that is the number of ways of picking 2 days for exam, and therefore, Bx is equal to k choose. So, we had written n equals k, so n is equal to n, or ak equals k. Bx equals k choose 2 x raised to k summation k equals 0 to infinity. So, k equals 1, k equals 0 terms are going to be absent. So, this is going to be equal to 2 into 1 by 2 into x square plus 3 into 2 by 2 into x cube plus 4 into 3 by 1 into 2 into x raised to 4 and so on. Okay. So, these expressions we need to somehow obtain a nice closed form solution for this, and that is what we will do. So, all these are very nice expressions whose closed forms can be easily obtained from the following generating function. Let us say Tx is this particular sequence 1 plus x square, so on, okay, and Tx clearly is 1 by 1 minus x. Now, if you differentiate both sides, what we will get is 1 minus x raised to 2 is equal to 1 plus 2x plus 3x square and so on. That is pretty much same as Ax, just one x is missing. So, therefore, from this we can conclude that Ax is equal to x by 1 minus x the whole square. And if you differentiate this once more, what we will get is 1 by 1 minus x raised to 3 into 2 is going to be equal to 2 plus 3 into 2 x plus 4 into 3 x square and so on. So, this is almost the same as Bx, but there are few missing terms. So, if you just supply the missing terms, I mean what all that one has to do is multiply by x square, okay, or so multiply both sides by x square by 2, we will get Bx is equal to x square by 1 minus x the whole cube, and therefore, Cx is just going to be the product of Ax and Bx, that is going to be x cube by 1 minus x raised to 5. So, now what we know is this summation that we were looking at, which gives us the nth term of the number of ways of splitting the semester, is a sequence whose generating function has a simple form x cube by 1 minus x raised to 5. Okay. Now, how do we find the nth term of 1 minus x raised to 5? You can use the generalized binomial expansion. So, we just need to expand 1 by 1 minus x raised to 5 and then shift everything by 3 because there is an x cube. We need to find the x raised to nth term inside this. If you find the x raised to nth term inside this, that is going to be equal to the x raised to n plus third term in the expansion of 1 minus x raised to minus 5. Okay. So, let us look at how we can write this as a sequence. So, again we will look at this particular equation. If we differentiate it once more, what we will get is 2 into 3 by 1 minus x raised to 4 is equal to 3 into 2 plus 4 into 3 into 2 into x plus so on. If we differentiate yet another time, you will get 2 into 3 into 4 by 1 minus x raised to 5, that is the left hand side, that will be equal to 4 into 3 into 2 plus 5, 4, 3, 2 into x plus so on. Okay. And what we need is this multiplied by x cube. Okay. So, we can write this in the following manner: 2 into 3 into 4 by 1 minus x raised to 5 is equal to 4, 3, 2, 1 plus 5, 4, 3, 2 into x plus 6, 5, 4, 3 into x square and so on. Okay. So, if you just multiply by x cube on both sides and divide by 2, 3, 4, what we will get is 4, 3, 2, 1 divided by 1, 2, 3, 4 plus 5, 4, 3, 2 by 1, 2, 3, 4 into, so that will be an x cube into x raised to 4, so on. So, basically this is going to be equal to summation over n going from, let us say 3 to infinity x raised to n, n plus 1 choose 4. Okay. So, that would mean that the coefficient of the nth term is n plus 1 choose 4. So, this will apply only when n is greater than or equal to 3. The other terms are going to be 0, rightly so, because if you want to split with the first part having 1 holiday and the second part having 2 holiday, you need at least 3 terms. Okay. So, that is basically the answer of that combinatorial identity, summation k into n minus k choose 2, k going from say 1 to n minus 2. This will be equal to n plus 1 choose 4. Now, let us look at one more problem. We will not do it in this detail, we will just quickly rush through the problem. We again need to split the semester into 2 parts. So, semester has n days and now any day of the first part can be chosen for a surprise test. So, the possibilities that we have is there could be surprise test on all days, there could be surprise test, there could be no surprise test, that means every day I mean you do not have any surprise test, that is a possibility. And in the second part there could be a surprise holiday, any day can be chosen as an off day. Okay, rather strange way to have a semester, but that is our problem. We have, so we have n days and these n days must be split into 2 parts, and the first part, so you could have let us say test or no test, okay, any choice is okay, and in the second part you could have a working day or an off day, and that could be chosen in any way that the dean pleases. So, we want to know how many ways are there to organize such a semester. Okay. So, again if Cn is the number of ways, okay, Cn is going to be summation k going from 0 to n a n, so a k b n minus k, where a k is equal to number of ways of organizing the first part, and bk is the number of ways of organizing the second part. And what we know is C generating function of Cn, that is going to be equal to Ax times Bx. So, Ax is the generating function of the sequence An, and An is going to be 2 raised to n, because if you had n days or k days, every day you could either have a test or no test. There are 2 possibilities, total there are 2 to the power k possibilities, and therefore, Ax is equal to summation 2 raised to k x raised to k, k going from 0, this is going to be 1 by 1 minus 2x. And Bx is also exactly same thing, instead of surprise test we have an off day or a working day. So, this is also going to be equal to Bx, and therefore, we can write Cx is equal to 1 by 1 minus 2x the whole square. Okay. Now, from this how do we extract out the nth term? We could again use binomial theorem or the binomial expansion, and from that we can infer, but here there is an easy way. So, if we denote, so Cx is equal to a prime x by 2. Okay. If you take a prime, so a prime x is nothing but 1 by 1 minus 2x the whole square into 2. Okay. So, Cx is also equal to a prime x by 2. Okay. So, Cn is equal to half of the nth term of a prime x, okay, and Ax is equal to 1 plus 2x plus 2 square x square and so on is equal to 2 raised to k x raised to k summation. So, a prime x is equal to 2 raised to k into k into x raised to k minus 1. So, a prime x by 2 is equal to 2 raised to k minus 1 into k into x raised to k minus 1, and therefore, the nth term of this of a prime x by 2 is nothing but coefficient of x raised to n, that is going to be equal to 2 raised to n into n plus 1. Okay. So, we can conclude that, so for Cn is equal to n plus 1 into 2 raised to n. So, we have seen two examples where the use of products of generating functions to compute combinatorial quantities. So, the third example is a more classical example. This involves what is known as the Catalan numbers. So, Catalan numbers arise in a wide variety of contexts. Here we will see two examples, both of them are essentially the same combinatorial object masquerading as different things. The first thing is balanced parenthesis. Okay. So, we have, let us say, n pairs of parentheses. Okay. So, left and right parentheses there are, so this is one pair and we have n such pairs, okay, and we want to rearrange them in any manner, but the result should be a balanced parenthesis. That means that should come out of parenthesizing some expression. In particular, all it means is every left parenthesis, I mean a right parenthesis should come only after the left parenthesis, and the total number of left parentheses should always be greater than or equal to the number of right parentheses. Okay. So, left is greater than or equal to right. Okay. If you look at the number of left parentheses that has appeared in any prefix of your parenthesis, the number of lefts are going to be greater than or equal to the number of right, and total count should be equal. Okay. So, this is an example of a balanced parenthesis. So, here I mean at the start there is 1 and the number of left is always greater, but except at the very end where they become equal. Now, if you take this, here the count becomes, the left minus right becomes 0 at this point, and 0 again here, and finally when the full expression is read, at that point also it is 0. Okay. So, we want to find the number of ways of arranging these parentheses so that it is balanced. So, let us take the example where the number of pairs n is equal to 2. So, this is one way and another way would have been, and these are the only possible ways, because it should begins with the left, the next one can either be a right or a left. If the next one is a left, there is this possibility. If it is a right, then the only way the whole expression can be made balanced is by having, so these are the only two possibilities. When n equals 3, you have this as one possibility, this is yet another possibility, So, when n is equal to 3, there are these 5 possibilities, and we need to compute the value on the number of balanced parentheses for the general n. It is a very similar problem, which is also known as the gambler's ruin or the drunkard's walk. So, this is the x axis denotes time and y axis denotes the amount of money or the position from where you have started. Just call it as amount of money, and you start with 0 units of money, and at each time the total amount of money that you can have will either go up by a unit or come down. Okay. So, you can go up and then again up and then again up, and then you could come down Okay. So, here is a sequence of steps such that you started at time 0 with 0 amount of money, and after 10 units of time you are still at 0, but in between you had gone negative. We want to find the number of ways of starting at 0 when at time 0 with 0 amount of money and ending at 0 after, let us say, 2n steps. It has to be always even number of steps, because starting at some place and ending at the same amount of money, the total number of steps that you would have taken should be even. So, after 2n steps, how many ways are there by which you can reach the same starting position? And the additional constraint is you should never go negative. Okay. So, both these problems, if you think of this as a drunkard walk, it is essentially a drunkard is starting at some particular position. Each step he takes, he either goes one step closer to, it is a one dimensional walk, he is going towards his home or coming back, but he is never allowed to be at distance greater than what he was from his home at any point of time. Okay. So, under that restriction, what is the, he is never allowed to go towards the negative side of the axis. So, how many ways are there to do this? Okay. So, again we will use the notion of generating functions, but it is slightly more trickier than what we had done in the earlier case. Okay. So, Cn, let us say, denotes the number of ways. Okay. So, look at all possible steps that you can take. So, this we will call as a bad walk, whereas if you had the following walk, this is a good walk of length 8. Okay. So, we want to find the total number of good walks. We will also define what is known as a very good walk. Let me just give an example of a very good walk. So, this is an example of a very good walk. I have informally defined what is a very good walk, we will do that shortly. Okay. So, let us look at any of these walks, we can split it into two parts. The first part will consist of a very good walk and the second walk will be a good walk. Okay. So, and we will essentially be taking the convolution of these two things to get to our answer. Okay. So, let us look at some particular walk. Two things can happen. It starts at 0 and then it hits the x axis at some point of time and then again goes up, or it hits the x axis only at the very end. Okay. So, let us look at the first time when it hits the x axis. Okay. So, look at the first time when a walk comes back to x axis. Now, if you look at the remaining portion of the walk, that is essentially just a good walk of the same length. Okay. So, we can think of every walk as split into two parts. The first part is start at 0 and hit the x axis at some time I. So, this I is hitting the x axis for the first time, and then remaining portion. Now, the remaining portion has to be exactly same type of the walk, or it just has to be a good walk. What about the first portion? The first portion is also a good walk, but it is a special kind of good walk. In the sense, this portion, so if you take this as, let us say if you denote by I, the time when it first hit the x axis, now any walk of length 2n minus I. Okay. You take any good walk of length 2n minus y, put it here in this region between I and 2n, and take these two portions, you will essentially get a good walk. Whereas, if you take this region 1 to I and replace it with a good walk, you will not get something of the kind that we are talking about, because what we want here is that the walk should not have touched the x axis at any point of time. Okay. So, the number of ways of constructing walks by combining these two walks is not going to be just the product of two simple good walks. Okay. It is a product of a simple good walk and something which is very good, in the sense it has never hit the x axis. Okay. So, we will formally define what is a very good walk. So, a very good walk is a good walk that does not hit the axis except at the start and at the end. Okay. So, good walk, we know its generating function is the number of good walks of length Cn, its generating function is going to be, let us say, Cx. What is the generating function of very good walk? Okay, that is what we need to determine. And if we say that the generating function of very good walks, suppose we call it as dx, then since the first, for n equals 0 the split does not work, we will have to write Cx minus 1 is going to be equal to Cx times dx. Now, from this equation we can solve for Cx, but when assuming we know what is dx. So, let us first compute the generating function of dx. Okay. So, let us look at the good walks of length dx, of length 2I, and these are the very good walks of length let us say 2 times I plus 1. What we will do is, in order to compute this, we will show that the number of good walks of length 2 times I minus 1 is equal to number of very good walks of length 2i. Okay, why is this so? So, let us take a very good walk of length 2i. Okay, so that will start, any walk, good or very good, has to start with an upper, with a positive arrow, and the last one of that should be a downward arrow. First one should be upward and the last one should be downward, and this entire length is going to be, let us say, 2i. Okay, and the very good walk has the additional property that it never touches the x axis anywhere in between. So, let us take a very good walk and strip it off the first and the last moves. What you will get is some walk of length 2 times I minus 1. Okay. So, if we look at the set of all very good walks of length 2i and all good walks of length 2 times I minus 1, we can have a 1-to-1 correspondence. Okay. I mean, take a particular walk and strip it of its first and last moves. So, if you strip this off, you will get something on the other side. Okay. If you take two distinct elements of the very good walk and strip it of its first and last elements, what you get will be distinct elements of the good walk. Further, if you take any good walk and add these first and last moves, you will get a very good walk. So, every element of GW can be generated from VGW, and every element of VGW gives rise to a unique GW, and therefore, these sets are in 1-to-1 correspondence. So, that would also mean that the generating functions can be quickly computed. So, now if you denote di by the ith element, I mean if you denote di by di the number of very good walks of length 2i, then di is going to be equal to ci minus 1, and therefore, the generating function dx is just going to be equal to x times cx. Okay, so, that is the key property. So, from this we can write cx minus 1 because the split works only for walks of length greater than or equal to 1. So, this is going to be equal to x times cx times cx. Okay. So, we can rewrite this as x times cx square minus cx plus 1 equals 0. Think of cx as a variable, and if you solve the quadratic equation involving cx, you will get cx is equal to 1 minus under root 1 minus 4x by 2. Okay. So, when you solve the quadratic equation, there are two possible roots, but only one root will make sense for this particular generating function, and you can check that it is the root with the negative sign. Okay. Now, we have the generating function for cx. From this we can obtain the closed form solution. So, 1 minus 4x raised to half, you can use binomial expansion, that will have a 1 as the leading term, and that will subtract from this 1, and therefore, the constant term vanishes. Now, when the constant term vanishes, every other term will be an even term, and you can show that cx will be of the form 2n, choose n into 1 by n plus 1. So, this is the nth Catalan number. This number has a name, that is the Catalan number. We can see that many other recurrence of which gives rise to generating functions of this kind gives Catalan number as the answer. Okay, we will stop here.